Hello friend, today we will discuss the second lecture of air refrigeration system. In previous lecture we have discussed the COP of air refrigeration system, its PV and TS diagram and its compressor efficiency and expander efficiency. And today lecture we will discuss about the ramming process in aircraft, ramming process derivation or equation, bootstraps refrigeration system and reduced ambient refrigeration system. Also we will discuss regenerative refrigeration system and dry air rated temperature dart, which is called. The lecture outcome will be, if the person is listening and watching this lecture, he will understand the basic principle of ramming process in air refrigeration system, different type of air refrigeration system and calculation of various parameter. Let's see here what is the ramming process in aircraft refrigeration cycle. Ramming process, you can see here in TS diagram, it will have from 1 to 2 is the ramming take place. How it is taking place? When the aircraft is flying with the high speed in atmosphere, the atmospheric air will strike or contact with the aircraft surface, then the air temperature and pressure increase suddenly, and that process is called the ramming process. In that, when air is strike at the surface of aircraft, the temperature become stagnant or constant, and that temperature is called the stagnation temperature, where you can have the T2 dash and T2 is called the stagnation temperature. Okay, so here you can see here in this in upper diagram there is aircraft, if you see, and the here the T1 is the outside aircraft or ambient condition, where air is coming to the aircraft surface, and that after that the air temperature become T2 and pressure become P2, and that air is called the rammed air. After that, rammed air goes to the C, which is main compressor, and after main compressor the air 90 or 80% air goes to the main combustion chamber, or you can say aircraft engine, or 10 or 20% of air we can withdraw for the air conditioning unit. For in the so here you can see in the 3 dash in HEX, that is the heat exchanger. So 10% of that air we withdraw to the heat exchanger, then it goes to the TC, the cooling turbine, and after that it goes to the cabin. So if there is 100% air goes to the aircraft, then 80 to 90% air is consumed by the aircraft engine, and remaining air is we withdraw for the air conditioning unit. Okay, so here you can see the TS diagram. 1 to 2 dash is the ideal ramming process, and 1 to 2 is the actual ramming process. After that actual process, 2 to 3 is the actual compression of 2 to 3 dash is the isentropic compression, and from 3 to 4 is the constant pressure cooling process. 4 to 5 dash the isentropic expansion or ideal expansion. 4 to 5 is the actual expansion, and 5 to 1 or eta here it is representing is the supply of air take place inside the cabin. So this is the temperature entropy diagram for the aircraft with the ramming process. So here what happen, the work we are giving in the 1 to 2, 2 to 3, and work we are taking from the 4 to 5. So total net work will be ramming work plus compressor work minus expansion work. Then we need to derive the equation or relation for the ramming process. So we apply the energy equation for the diffusion process from 1 to 2. So from the 1 to 2, the at the initial there is the energy in the air, which we represent by the H1, and what have the velocity of the air. So the kinetic energy plus c square by 2, and that energy after striking convert in the H2. So the equation become H2 equal to H2 dash, because this line is the horizontal line. Here you can see, okay, here T2 dash and 2 is the stagnation temperature or constant temperature. T2 dash equal to T2. So we need to have here this relation, H2 equal to H2 dash equal to H1 plus C square by 2. Okay, and that enthalpy we can convert in the Cp delta T, because del H equal to Cp delta T. So Cp T2 equal to Cp T2 dash equal to Cp T1 plus C square by 2, where c is the velocity of aircraft. Okay, and further we can calculate or Cp cancel out. So T2 equal to T2 dash equal to T1 plus C square by 2 Cp, that we can assume equation 1, and further simplify by dividing the T1. So it become T2 dash by T1 equal to 1 plus C square by 2 Cp T1. So this relation is for the ramming process, when you can, or in equation 1 itself you can calculate the temperature T2 if the T1 and velocity of aircraft is given. Okay, so this equation we use generally to calculate the temperature or ramming temperature. Okay, when the initial temperature and velocity of aircraft is given. Further, if in term of Mach number we need to calculate, we can calculate likewise. So here further equation become T2 dash by T1 equal to 1 plus C square by 2. Here we are replacing Cp by the gamma R by gamma minus 1, and that is term Cp, and T1 was already there, so it become 2 gamma R by gamma minus 1 into T1. Okay, further we can simplify this by T2 dash by T1 equal to 1 plus gamma minus 1 by 2 C square divided by A square. Here you can see A square, how it is come, A equal to the under root gamma R T1, which is called the acoustic velocity. Okay, so this is the relation generally used for the ramming process in term of Mach number. So further in term of Mach number, it become T2 dash by T1 equal to 1 plus gamma in bracket gamma minus 1 bracket close by 2 m square, where m is the Mach number, and T2 equal to T2 dash is the stagnation temperature of ambient air. Okay, so this equation generally used when the Mach number is given. Next, sometime examiner will ask the ramming efficiency. So and also it asks in the calculation in the numerical. So what is the ramming efficiency? It is defined as the actual pressure recovery to the ideal pressure recovery. Actual pressure recovery where it is happen in the isentropic, in actual process. In ideal pressure recovery where it is even in the isentropic process. So in term of P2 P1, it become eta R equal to P2 minus P1 divided by P2 dash minus P1. So this is the ramming efficiency, where you can see P2 minus P1 is the pressure increasing or recovering in the actual process. Okay, here you can see here 1 to 2, and 1 to 2 dash is taking place in the ideal ramming process. So where P2 dash minus P1. Okay, so this is the ramming efficiency. Next, the examiner can ask the what is the ramming work. Okay, so WR equal to Cp specific heat multiply Ti, which is the inside cabin temperature, minus T5, or T5 is the after expansion from the turbine, bracket close, kilojoule per kg. Similarly, next compressor work in this, so it is between 3 to 2 to 3. So Wc equal to Cp in bracket T3 minus T2 bracket close, kilojoule per kg. Similarly, expander work where expanding expansion is taking place between 4 to 5, so it become we e in suffix equal to cp in bracket t4 minus t5. Net work or total work WR, ramming work plus compressor work WC minus expansion work WE. Refrigeration effect RE equal to Cp multiplied Ti minus T5 kilojoule per kg. Okay, so these are the terms generally need to calculate in the numerical. Then there are different aircraft refrigeration cycle. In that you can have, first was the simple aircraft refrigeration system. In that simple process like ramming, then compressor, then heat exchanger, and then expansion, then air turbine. Like this one is the for, you can say this is for the simple aircraft refrigeration system, okay, or simple cooling aircraft refrigeration system. Okay, so one type is that. Then next you can have the bootstrap refrigeration system, and in this system there are two heat exchanger instead of one. Okay, and it also have the two compressor, like one is the main compressor and another here is the secondary compressor, which is driven by the turbine of the cooling turbine, which is driven by the cooling turbine, you can say. And this system is suitable for the high speed aircraft. Okay, and exceptionally high altitude, you can say. So generally this used for the high altitude. Okay, then another is the regenerative system. In next slide we will discuss about the TS diagram of the bootstrap. Here you can see the bootstrap system, where the ambient air is coming from the ambient and goes to the aircraft, where it ramming take place, ramming process will take place. From that it goes to the main compressor, where the 80% air goes to the combustion chamber or aircraft engine, and remaining 10 or 20% air we draw for the AC unit or refrigeration unit. So from main compressor the air goes to the first heat exchanger here, then it goes in the secondary compressor, then it goes to secondary heat exchanger. So it have two heat exchanger, two turbine, main compressor and secondary compressor, then it goes to the compressor. Okay, and heat exchanger you can have the two floats. So one is the that ramming air, it's coming from the main compressor, and for cooling medium the before main compressor the ram is there, so we withdraw from here ram air because it is still cooled. Okay, so it work as a cooling medium in the first heat exchanger and second heat exchanger. Okay, and after second heat exchanger the air goes in the cooling turbine, where the expansion is take place and the air temperature will reduce to the desirable condition and is sent to the cabins of the aircraft. Here you can see the TS diagram of bootstrap refrigeration system. 1 to 2 is the ramming process, 2 to 3 is the compression in the main compressor or isentropic compression, then 3 to 4 is the constant pressure cooling take place in the first heat exchanger. Then again secondary heat exchanger, there is again pressure and temperature will increase from the 4 to 5. Then 5 to 6 the secondary heat exchanger is take there, where the constant pressure heat rejection is there. After 6 point there is second turbine, or where the expansion is take place to the desirable condition, or it reduce the temperature and pressure for to the desirable point, and after that it's sent to the inside the cabin where the I point is there. Okay, so this is the TS diagram of the bootstrap system. Then reduced ambient system, before that it was the regenerative is not much different from the simple refrigeration system. Regenerative system, it have the two heat exchangers. Generally in regenerative system, part of the cooled air from the cooling turbine is used to pre-cool the air entering the turbine. As a result, much lower temperature are obtained at the exit of the cooling turbine, and the regenerative system is good for both ground cooling as well as the high speed aircraft. Okay, but generally it is used for the ground cooling. Okay, so that is not important, generally not asked, because it's similar to the simple aircraft refrigeration system. Okay, and third one is the reduced ambient system. The reduced ambient system is well suited for the supersonic aircraft and rockets when the ram air temperature is too high. Okay, so it need to cool down, so it generally have one extra turbine. So generally this system has the two turbine. So here you can see reduce ambient. The ambient air come inside and get rammed air, then it go to the main compressor where it goes to the heat exchanger, then it is go to the turbine, then it goes to the cabin. But here you see in the heat exchanger the cooling air is coming from the T1 turbine, which is coming from the rammed air, because here the rammed air directly you cannot use, because with the high speed of aircraft the rammed air temperature is too high that we cannot use in the heat exchanger directly. So first it need to be go through the turbine where the expansion is take place and the temperature reduced, then we use in the heat exchanger for the cooling purpose. Okay, so that is the main difference here. And from the heat exchanger, the ram the air which is coming from the turbine goes to the exit, and the air which is coming from the main compressor goes to the secondary turbine or another turbine or cooling turbine, where it further reduce the temperature and pressure to the desirable condition and supply to the cabin. Here the auxiliaries, fans and other system are running with the help of the turbine, two turbine. Okay, T1 and T2. So here you can see the TS diagram of the reduced ambient. 1 to 2 the ramming process taking place. 2 to 3 the isentropic or actual compression is taking place in the main compressor. 3 to 4 constant pressure heat rejection is taking place. 4 to 5 the expansion taking place in the secondary turbine or T2 turbine, and then 5 to 1 the expansion air is supplied to the cabin. Next term is the dart. Dart generally used to compare the different type of aircraft refrigeration system, and its full form is the dry air rated temperature. If the definition, it is defined as the temperature at exit of the cooling turbine without moisture. I am repeating once again, it is defined as it is the temperature at exit of the cooling turbine without moisture. It is used to compare different type of air refrigeration system. Here you can see with the help of the dart we can compare different refrigeration system or aircraft refrigeration system. In y-axis we place the dart in degree centigrade, where you can see minus 100 degrees, minus 60, minus 20, minus 10, minus 10, after that 60 and 100 degree centigrade. In x-axis you have the Mach number, which can be vary from 0 to 2.5 or 3 or 4. Okay, so in simple ground cooling, what is the low temperature generally minus 20 to 60 or 50. So the simple and regenerative system have the range, regenerative system have the range to minus 22 Mach number less than 1, you can see. Similarly regenerative system have much lower temperature like minus 70 and the Mach number 1.2. Similarly bootstrap refrigeration system have the range very low temperature minus 70, minus 80, you can see, and high speed like 1.2 or 1.3. So generally bootstrap generally used for the high altitude where the very low temperature is there. Okay, okay, so that point must be remember. The bootstrap system is suitable for the high altitude aircraft. And reduced ambient, here you can see it can be used for in range of minus 60 to Mach number 2.4 or 3 or 4. Okay, so reduced ambient system is generally suitable for the very high speed aircraft which have the speed of more than 2.2 or 2.5 Mach. Okay, so here is the comparisons. So that's all today, I think. Okay, thank you very much. Have a good day. In next lecture we will start vapor compression refrigeration system. Okay, and for the numerical of this unit, I think you need to refer some book like CP Aurora, and you can have some NPTEL notes also. Okay, and also Khurmi you can prepare, and Rajput you can refer the refrigeration air conditioning. Okay, so do some numerical exercise, then you will get to know much more. Thank you very much. Have a good day.